Hi, we're going to start on a topic of forces today. Let's just make sure my pen is working. Should have said that before, really. Yeah. Okay, so we're going to be able to represent forces as a free body diagram by the end of this lesson. But we're going to start off with just some basic motion questions, and we're going to review some of those things. If I travel 4.5 miles and it takes me half an hour, what speed am I traveling? If you travel 70 kilometers in 2 hours, what is your average speed? If you walk for 1.5 hours at an average speed of 4 miles an hour, how far have you walked? A car is traveling at 70 miles an hour. It travels for half an hour. How far has it gone? A bus took 20 minutes to travel 10 miles. What was its average speed? How long would it take a bike to travel 20 miles if the average speed is 60 miles an hour? And if a car is traveling at 50 miles an hour, how long would it take for the car to travel 12.5 miles? So, pause, answer the questions, and I'll go through them in a minute. Okay. Have you done that? Excellent. You probably need a calculator to work these out, or just be really good at the maths in your head. So, if you remember the equation, we've got speed is equal to distance at the top over time. And obviously you could rearrange that depending upon what it is you're asking. So the first one, it says I'm going 4.5 miles in half an hour. 4.5 all over half an hour equals 9 miles per hour. If you travel 70 kilometers in 2 hours, same equation, 70 over 2 equals 35 kilometers per hour. If you walk for 1.5 hours at an average speed of 4 miles an hour, how far have you gone? So this time it's speed times time. So 1.5 multiplied by 4 is 6 miles. Nice. A car is traveling 70 miles an hour. It travels for half an hour. How far has it gone? Okay, so it's going, speed is 70 multiplied by 0.5 equals 35. A bus took 20 minutes to travel 10 miles. What was its average speed? So distance is 10. Oops. Why's that stopped? 10. Man. Pen. Come on. Pen pierce will stop working again. So you do the distance of 10 miles divided by the time, which is 20 minutes. If we're doing it in miles an hour, 20 minutes is a third of an hour. So divided by a third. So 20 divided by 0.3. Been a complete donut with my calculator. 60 miles. How long would it take a bike to travel 20 miles if the average speed was 60 miles per hour? Well, it's basically a third of an hour. That's a third of it. And if a car is traveling at 50 miles an hour, how long would it take for the car to travel 12.5 miles? It's difficult to do this without my pen. So, come on. Right, I think I've got it going. Yeah. If a car is traveling at 50 miles per hour, speed is 50. How long would it have to take 12.5? So it's 12.5 divided by 50. 12.5 divided by 50 is 0.25, a quarter of an hour. Okay. Right, so when we're representing forces, we represent it normally with a force diagram. You've done this before, Key Stage 3. You've done this at Year 9. We're doing it again at Year 10. All of these things should be fairly simple and fairly obvious, but let's just review. If you put an arrow, the direction of the arrow shows the direction of a force. Direction's important. What does that mean force is? It's a vector. The length of the arrow is proportional to the size of the force. So we look at these two scenarios. We have air resistance, and that is pointing up. And we have weight, and that is pointing down. Both of these are forces. The force of air resistance is going up. The force of weight is going down. But the difference is the air resistance arrow is shorter than the weight arrow. So therefore, the air resistance is a smaller force than the weight force. So this one, the weight is pulling down with a larger force than the air resistance is pushing up. So two forces acting on this ball, we have the weight and air resistance. Two forces that we're showing on this ball are the weight and the air resistance. There are other forces, but this is nice and simple. Now, these two forces are two different types of forces. These forces are actually, these forces are actually, the difference between the forces are contact and non-contact. Now, this might seem strange for you, but air resistance is actually a contact force. And that's because the air particles have to actually hit the ball to have an effect. Although when you look around you, you can't really see the particles that are in the air. We know they're there because we're breathing the air, and you experience air resistance as you're driving or you're cycling on a bike or going somewhere. If you're going fast, you feel more wind in your face. That's you hitting the air particles faster. So you get more air resistance. You have to actually hit the air. You have to kind of crash into the air to feel the air resistance. Whereas the weight, you don't have to be touching. So your weight is due to the gravitational attraction of the Earth. You don't have to be on the Earth to have weight. If you're flying above the Earth or falling from a great height, you have weight. The Earth doesn't have to touch you. That is a non-contact force. So forces can be divided into contact and non-contact. Contact, the particles have to actually touch for the forces to have an effect. Non-contact, they don't have to touch. The forces of attraction is strong enough to pull them together or push them apart, depending upon what they are. A contact force, they have to touch to have an effect. And things like air resistance is a contact force, although you can't see it. Weight is not a contact force. Weight is just due to the gravitational attraction of the Earth. You don't have to be touching the Earth to have weight. If you are touching the Earth, it will still have an effect on you, but you don't have to be touching for that to have its effect. In fact, I'll summarize some of the forces. There are loads of contact forces, but there are only 4 non-contact. The non-contact are the gravitational force due to the mass of a planet or the sun or something. Magnetism is a non-contact. You know, if you hold 2 magnets near each other, they can just be drawn together in an attractive way. Static electricity actually is a non-contact. Same, you rub a balloon against your hair and you hold it above your head. They don't have to touch for the balloon to kind of be drawn, your hair to be drawn up towards the balloon. And the nuclear force is a force that happens inside the nucleus and atoms. Don't have to worry about that one just yet. Contact forces, example of contact forces, friction, when 2 surfaces rub against each other. We just mentioned air resistance. Upthrust is another one, which is almost the same as air resistance, but you can have upthrust in water. Tension, when you're pulling on something to like pull a rope at 2 ends, that's tension. And reaction, that's the force that stops you sinking into the ground when you're sitting on a chair, or the opposite of almost the weight of something. If there's anything to note for today, perhaps this is it. The difference between contact and non-contact, and here are some examples. They are the only 4 non-contact forces. So let's have an example of some of the forces that are acting on a fish. We have upthrust, we have friction, we have weight, and we have thrust. So what do we know about these forces? What can we tell? From the arrows, 1, they're all working in different directions. In fact, they're all working almost in opposite directions. We can also tell that the weight and the upthrust are the same size. Look at the size of the arrows. They're opposite, but they're the same. And so is the thrust and the friction. They are the same size. So in overall, these forces are actually balanced. We'll come to that in the next lesson. But we can tell that the forces of weight and upthrust are the same, and the forces of friction and thrust are the same, but they're just in opposite directions. Okay, write this down, pause, write this down, and then I'm going to go through what it means. Pause, write it down, unpause when you're done. Done? Excellent. So we're going to do a particular type of force diagram. It's called a free body force diagram, and they're showing the forces acting on a single object. When you're doing this, it's okay to draw the object as a dot or a circle or a box. You don't have to draw a car or a person. You can, you don't have to. You identify the non-contact pairs. For example, weight due to gravity. You identify the contact pairs. Could be reaction or air resistance. And then you focus on a single object. Just draw those forces. So let's do an example of something on a book on a table. So first of all, non-contact forces. The non-contact forces with a book is weight. So the book has a weight because the earth pulls it towards it. It pulls it towards its center. So the force of the earth on the book, that is a non-contact force, pulling down. Equal, actually, the earth is pulled towards the book. Strange one, because the book itself has a gravitational attraction, but it's very small, so the earth doesn't really notice. So the book is pulled towards the earth, and the earth is pulled towards the book. The book is on the table. The book isn't dropping through the air. So actually, the table pushes up against the book. The force of the table onto the book pushes up against force. That would be called the reaction force. The book also pushes into the table due to its weight. Let's see if I can move my face. So to do a free body force diagram, you just take the forces on one object. We take the book, and we have the force of the table on the book is that arrow going up, and the force of the earth on the book. And those are the two forces we drew. So there were 4 forces involved, but we only picked the ones that were happening to the book. And that gives us our free body diagram. So when you're drawing one of these diagrams, you work out all the forces and then just focus on something and draw the forces relating to that. So the force of the table on the book and the force of the earth on the book. Not the forces by the book, but the forces on the book. So this previous thing there, the one talking about the force of the earth on the book, is due to Newton's third law. Now, probably in primary school or people who aren't good at physics might use this as for every action there is an equal and opposite reaction, which kind of is a very simple way of doing it. But actually, in reality, it's a bit more complicated than that, or it's a bit more specific, not complicated. So what you have to say is, if object A exerts a force on object B exerts an equal and opposite force on object A. I'm going to go back to this diagram here. So here, if the book is object A, oh, why does this pen keep stopping? And the earth is object B. And so object A, no, A, and this is object B. Okay, so if object A exerts a force on object B, so object A, the book, exerts a force on the earth. It pulls it towards it. Object B has to exert an equal and opposite force on object A. So you've got the earth pulls the book pulls the earth. So when you're writing Newton's third law, the forces must be the same, but they must be acting on opposite objects. So the book exerts a force on the earth exerts a force on the book. Now in this situation, book weighs very little, the earth weighs 6 times 10 to the 24 kilograms, quite a lot. So a tiny force on a massive mass has no effect, whereas a small force due to its weight, but on a really, really, really small mass, will have quite a big effect for causing the book to fall towards the Earth. The Earth doesn't really move. So for Newton's third law, if object A exerts a force on object B exerts an equal and opposite force on object A. Again, Newton's third law, it's a good thing to write down. Go on then, write it down. I'm going to pause and try and get my pen to work. So, here we have another situation. Now, you've got two skateboarders, John and James, and if this situation, what happens is, John is pushing James. So they're both standing still, holding hands in a strange way, and John pushes really hard on James. What's going to happen? Now, the first thing you might think of is James is going to fly back, which kind of makes sense. But if we apply Newton's third law, if John pushes on James, James has to, well, it does, because of Newton's law, James actually exerts an equal yet opposite force on John. So even if James just keeps his arms still and doesn't physically push, doesn't move, and John is the only one that does this, what happens is the force that's exerted by John on James is kind of mirrored, and you get exactly the same force, but in the opposite direction, on James by John, on John by James. And so actually, what happens is, even though John was the only one that pushed, they both start moving in the opposite directions, and they both move at the same speed, assuming they're the same mass, that one's not heavier than the other. They will both move apart, not just James moves away. If you put a force on object A, then equal and opposite force occurs on object B, and they both move away. Okay, that was equal and opposite forces. Sometimes the forces are not equal, but they can be opposite. In this situation, we have a box, quite a large crate. In this situation, we have an arrow pointing to the left that says 50 newtons. We have an arrow pointing to the right that says 30 newtons. Even if we couldn't see the numbers, we could see that the arrow on the left is longer than the arrow on the right. And so, actually, what's happening is the force to the left is bigger than the force to the right. And so, what's going to happen is you'll get a resultant force in one direction. That means there's going to be more force to the left than there is to the right. The pen is still not working. Oh, it started again. Typical. So 30 newtons that way, 50 newtons that way, 30 newtons that way. And what you end up with is, in reality, a smaller arrow of 20 newtons that way. So if you're not sure how to do it, when you're doing forces, you do, with your arrows, you do tip to tail. So you draw one force, 50 newtons that way. And when you've got to the tip of that one, so I finish this arrow, you then draw the next one, starting from the tail of the next one. And so what happens is, because these two are pointing in the opposite direction, this bit cancels out, and all we're left with is this bit. So 50 this way, 30 that way, leaves us just 20 newtons resultant force. Oh, I've just drawn all over the text. That's pretty silly. I apologize. So in this situation, what's going to happen? We've got 10 newtons going down, 3 newtons going up. What's the resultant? So they're 2 in the opposite direction. So 1 is minus the other one. So 10 minus 3, 7 newtons. Oh, look how happy the worm is. Here we've got 20 newtons to the left, 20 to the right. What does that mean? 20 minus 20. Quick maths. 0. A happy chicken. Tricky, is it? Not really. We've got 6 newtons going to the left and 5 newtons to the left. So 6 plus 5 is 11 in that direction. You've got 4 in the other direction. So 11 minus 4 is 7. But is it this 7 or is it this 7? Well, the biggest force is in this direction. So the resultant is in that direction. And there's a snail on a football eating some cabbage. Of course. Whoa. Look at this one. Crazy. Okay, so here we have many forces. Let's look horizontally first. We've got 800 in this direction. What have we got in this direction? 450 plus 350. Quick maths realizes that is also 800. So the forces this way and the forces that way are now balanced. Up we have 400. Down we have 1000 plus 500. So 1000 plus 500 is 1500. Minus the 400 means, in total, we have 1100 going down. And there is a seagull to celebrate with us. So what were the consequences of the force acting on this boat? Look at the arrows. There are no numbers here, but what can you see? You've got air resistance and friction going back, weight, up thrust up, and thrust forward. These two arrows are the same. So there's no resultant force in these directions. These arrows, this, are basically the same as this. So overall, in this situation, all the forces balance. You could do it with arrows, or you could do it with numbers. Aha. So, chance for you to do a bit of practice. Can you work out numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Just write down the numbers and then write out and draw the arrow for the resultant force for each of these. Do it now. Pause, write the numbers and the arrows. Go. Have you done this? Excellent. Shall we check your answers? Right, first one. The force is 1 Newton and it's pointing up. The second one, 3 and 3, both cancel. Resultant force, 0 newtons. Third one, we have 20 newtons to the right, 30 to the left, so we have 10 newtons resultant to the right. And the next one, we have 15 to the left, because there's a larger force on the left. Number 5, 30 newtons up. Number 6, nothing, 0. Number 7, we have 15 to the left. And number 8, we have 2 to the left. Number 9, we have 2 going up. And we look at number 10, it seems more complicated, but actually you notice that up and down are already balanced. So there's no resultant force, meaning there's only 10 to the left. Right, now it's time for you to answer some questions. Name one contact force and one non-contact force on a high diver as they are falling through the air. High diver, someone who's climbed up a diving board and is going to dive down. What's a contact force and a non-contact force as they go through the air? Then can you do the same situation, but a contact force and a non-contact force as they enter the water? For the contact and non-contact forces you named in question 1, identify their equal and opposite force. That's the Newton's third law thing. And for the same question 2, do exactly the same. Might be easier to draw them, but you don't have to draw the diver, just draw them as a ball, maybe the water as well. Questions 11, 12, 13, 14. You can do it. Right. Sometimes it's not as simple as 2 going in opposite directions. Here we have an example of 2 forces at right angles. And there are different ways to work this out. And both of them are pretty easy. But if you don't know, it can seem tricky. The first one is to draw it. And I've seen this been asked in the exam. If you have a nice piece of graph paper, you can draw them by seeing that if you draw the 4 centimeter one and the 3 centimeter one, this one, the example here, they draw it into a square and measure across. But I think the simplest way is the rule for tip to tail. Tip to tail. So you draw 3 centimeters up, check. You then draw the next arrow exactly where the last one finished, check. So what's happened is the object has gone from here to here. So what you do is you measure this. And if your drawing is to scale, you'll realize that this is 5 centimeters. So drawing is 5 centimeters. So the scale one, you draw one arrow, and then when that arrow finishes, you draw the next arrow immediately from that point in the direction of whatever arrow it is, and then you measure the distance from the start of one to the end of the other. That's the scale drawing version. Those of you who are confident with maths might notice there's another way of doing it without having to draw. Pythagoras has a theorem, and it is, if you want to know the length of the hypotenuse, you sum the square of the other two and then take the square root. So actually, 3 squared plus 4 squared equals 5 squared, or 3 squared plus 4 squared square root equals 5. So you can either do it by scale drawing, or you can do it using Pythagoras' theorem. So what would it be for this one? You can either draw it like this, 4 centimeters and 6 centimeters. It's tricky to do on my computer like this. So, and what you would do is you'd measure this distance, but because I can't do that, I'll just do 4 squared, whoops, plus 6 squared, all square rooted, which I can't do in my head, which I probably should be able to, but 4 squared plus 6 squared, square root. And the answer is nice, handy 7.2 newtons. Okay, so here are some more questions for you to try. I'm not going to give you the answers to these straight away. You'll have to work them out, and I'll do answers in another lesson. So can you work out the resultant force for 15 to 20? Note, some of them, there's 3 forces. You'll have to work out the ones that are opposite first before you can do the right angle thing. Okay, and some of them are not trying to trick you, but they might be easier than they look. So pause, work out the answers. Again, it might be easy to sketch. You can do it by drawing. So if you want to do it as drawing, where it says 6 newtons, draw 6 centimeters and then a 2 centimeter. For example, if you're going to do it drawing, this one, you draw 6 centimeters this way and then 2 centimeters that way. And the difference is this. It doesn't matter which one you do first, because you could also do 2 centimeters this way and then 6 centimeters this way, and you notice the resultant is exactly the same. So it doesn't matter which one you start with. You can start with the long one and then the short one, or the short one and then the long one. It doesn't matter. The answer, these 2 lines, these 2 parallel lines are identical. So do it for all these. Pause, answer, go. Done? Splendid. And then the end. The last ones. Can you draw a free body diagram for a falling apple? Remember the contact forces, the non-contact forces, and then just focus on the apple. Explain why there'll be a downward arrow in every free body diagram that you draw for objects on the Earth. Easy. Draw a free body diagram for the table instead of the book. So that's going all the way back. Oh man, how many slides? Here. So this one, you drew the book on the table and we did the free body diagram for that. Whereas now, do the same thing, but do it for the book. And 4A, a force of 30 newtons is acting 40 degrees to the horizontal, using a scale drawing to find the horizontal and vertical components. Ooh, tricky. You might need a bit of graph paper, but I believe in you. And then you can use Pythagoras to check your answer. Okay, good luck. Love you. Bye.